Hey everybody, in this video we're going to be talking about predicting solubility. In particular, we're going to look at an example of CH2Br2 in water. And to explain the solubility here, we're going to be going through this series of steps outlined in the gray boxes. You could apply these exact same steps to really any set of potential solute and potential solvent that you're trying to analyze. Let's get started. The first thing to note is that typically the goal here is to predict solubility, but I'm going to actually cross that off because in this example we're not really making a prediction that has been done for us. We are being told from the beginning, in this case, that CH2Br2 in water is not soluble. So we're not really predicting, and instead what we're trying to put together is an explanation of why that is, right? Sometimes, you know, in the real world or in your chemistry class, that's what you're faced with. We already know that it's not soluble. The question is going to be why. So the first thing I want to do is make sure I know of these two substances, which is the solute and which is the solvent. The way that it's worded, CH2Br2 in water, implies that CH2Br2 is the solute, so I can label that formula over here in my solute column. In water implies that it's dissolving in the solvent, which of course is H2O. I'll label that here in the solvent column. So now I know exactly which thing is which. Part of this identification process is also knowing what types of substances you're dealing with. Are they molecules, ionic, metallic, and so forth? In this case, all of these elements are nonmetals, and anytime you're dealing with nonmetals bonded to other nonmetals, you're going to be talking about molecules. So CH2Br2 is a molecule, H2O is also a molecule, and anytime your substances are molecules, you're also going to want to know if they're polar or nonpolar. That's going to be key to the whole explanation of solubility, and the only way to do that is to draw out the Lewis structures of the substances. Now CH2Br2 is especially tricky in terms of its polarity and the Lewis structure that tells you about that polarity. If I draw out that Lewis structure now, I'll show you what a lot of students end up with, right? It looks like this. Once you draw that, the next thing you start looking for is electronegativity differences, which it has, right? There's some differences between carbon and bromine and carbon and hydrogen. And the next thing you look for to be polar is asymmetry. And the way I have this drawn, it looks completely symmetrical. And like a lot of the times when a molecule is completely symmetrical, your answer here is nonpolar. But the problem is with some Lewis structures, and this happens to be one of them, when there are four domains like this, the Lewis structure can be particularly deceiving in terms of how the molecule actually looks. The only way around this, anytime you've got four domains, or really you could substitute this rule out for any Lewis structure ever, you have to actually draw it in the shape that it actually exists. And for four domains like this, that is a tetrahedral arrangement, which is kind of like this little pyramid shape, or a tetrahedron is the actual geometric arrangement. And if you draw it out this way with the two H's and the two bromines, like so, you can finally see that while it looked symmetrical here, when I actually draw it out, I've got the bromines kind of over here on this one side and the hydrogens over here on the other side. This is actually asymmetrical. And because it's asymmetrical, I've got a polar molecule. That is one of the tougher things about this example and other molecules like CH2Br2. Water is a little bit more straightforward because this thing tends to just be known as polar or have this bent arrangement right from the beginning. But if you drew it out, that's how it would look. The point is, CH2Br2 is polar, and water is also polar. Okay, next up is, now that I know what my solute is, I can start to describe, so we're looking right here, the types of interactions that these solute molecules experience. How does one CH2Br2 interact with a second CH2Br2? So if you imagine another CH2Br2 here, how do they stick together? Since they're polar molecules, I know for sure that they're going to be experiencing dipole-dipole interactions. from one CH2Br2 to the next. I can also list London dispersion forces because all molecules, anything with an electron cloud, will experience a London dispersion force as well. Now I'm going to note one more thing here about these London dispersion forces. Typically, when you've got dipole-dipoles and LDFs, you end up ignoring the LDFs because they tend to be very weak. The dipole-dipoles tend to be the stronger of the two forces, so these LDFs don't matter much when a dipole-dipole is present. But in this case, I'm not going to ignore these LDFs because of one particular element, and I'll circle it in green, and that's the bromine atoms. When you get to an atom that is as large as bromine, and when I say large, I mean in terms of radius and its electron cloud, it fills up to, I think, the 4th energy level. It's a very large electron cloud atom that results in London dispersion forces that can start to be rather strong. So I don't want to label them as strong necessarily, but they're stronger than the typical London dispersion force. So maybe I'm not going to ignore the LDFs this time, and I'll need to be considering that CH2Br2 molecules have both of these types of intermolecular forces. If we jump over and do that same thing for the water molecules, of course water is going to experience dipole-dipole forces too, but these dipole-dipole forces are an extra strong type called hydrogen bonds, and we can just list the H bonds. You don't have to also list dipole-dipoles, and of course we can list London dispersion forces as well for the same reasons we just talked about. Now these LDFs, because all the atoms in here are very teeny tiny, we probably can ignore those. It's worth listing them, but also noting that they're probably not going to be as important in comparison to the hydrogen bonds. So now we get to the interesting part of this scenario. I'm going to look down here at the very last column, because usually at this point, once you know the types of interactions your substance is going to have, you can make that prediction. Well, one, we already made the prediction, it's not soluble. Two, let's go up to the top of the video screen and look at how you make that prediction, just so we can spot what's strange about CH2Br2 in water. It says that when a solute has similar types of interparticle forces to the solvent, it will be soluble. So what we've got here is a polar solute with dipole-dipole forces, and a polar solvent also with dipole-dipole forces. They're hydrogen bonds, but they're still dipole-dipoles. Typically, in a scenario like this, your answer would be soluble. However, if you recall back to the beginning of this video, we are being told that while you would predict that it's soluble, it's actually not. So we're trying to come up with why that might be, even though these two things do technically have similar types of interparticle forces. And the way to explain that is to fill out this last piece of information, the solute-solvent interactions, and compare their strengths to the solute-solute and the solvent-solvent. So here's how we do that. You've got to imagine we're trying to mix these two substances together. So here's my CH2Br2 molecules, and they're being combined with the H2Os. And in order to get a solution to form, these two molecules have to be able to stick to each other. They've got to be attracted with a significantly strong intermolecular force. So I'm curious, like, what that force even is. Now, they're both polar, so of course those forces are going to be dipole-dipoles, so we can list that. There's also going to be some LDFs, so we can list those. And I'm going to come up to the top of the video screen one final time to read this last statement in red, which tells us in some cases the solute-solvent interactions, the ones that we just labeled, are significantly weaker than the solute-solute and solvent-solvent, and in those cases a solution will not form. And we actually have one good thing going for us in this scenario. We already know that a solution will not form. And any time a solution will not form, then that statement in red must be true, that we know one thing for sure: the solute-solvent interactions are likely weaker than the solute-solute and solvent-solvent. If we look at what those forces are, this whole thing starts to make some sense. My solute-solvent interactions are dipole-dipoles and LDFs. If we look back and compare that to the solute-solute interactions, remember one of the things we noted. The LDFs between CH2Br2s can be significantly strong because of those bromine atoms. So that's one aspect of this. My solute-solute interactions are particularly strong in this case because of the LDFs between the solute particles. If we do the same thing, looking at the solvent-solvent interactions, which are hydrogen bonds, well known to be among the strongest types of interparticle forces. So my solute-solute interactions are these strong LDFs. My solvent-solvent interactions are these strong hydrogen bonds. My solute-solvents are just dipole-dipoles and LDFs, which indeed are going to be weaker than both of the things I've listed so far, and that is what your explanation would reference here. Anytime a solution is not soluble, it means for sure the solute-solvent interactions are weaker. In this case, I can even say why. It's because dipole-dipoles and LDFs are going to be weaker than these hydrogen bonds and these extra strong London dispersion forces. That also wraps it up for this video. Thanks a lot for watching.